work is done in high school. Most of my work is done in high school, but I also do some work in grade schools. And even in grade school, we can support kids in writing a claim and evidence and the reasoning. Now, the reasoning is going to not be as strong, but for instance, we in the third grade, there's a unit on balanced and unbalanced forces, and we ask kids to write a claim about what causes the car to start, stop, or change direction. And the children are able to say, the car started to move because I gave it a push, a force to start going forward. And my evidence is that the car would stand still until I pushed it. And the reason why is, in order to start something, you have to provide a force that's unbalanced with another force. Now, they don't quite say it that way, but they can give the reasoning. So I would encourage, even at a very young age, as we move forward, if we can support kids, we have to give them the structure, but if you give them a structure, I think you can really get kids to understand how to write a scientific explanation. So I would encourage, even from the first, you could certainly ask them, what do you think a scientific explanation is? And maybe Anne will talk about this on Thursday. I know Anne, in her work, she first has the kids in her classroom write an explanation without any support. And of course, it's incomplete. And then she gives them the structure, the scaffolds, and then they rewrite it. So I would, it's okay, I think, to start off just by write an explanation, see what they do. But then soon after that, you want to give them a support for writing a scaffold. Any other questions from yesterday that I can respond to? You can drop it in the chat, or you can just raise your hand and ask it. Okay, well, I'm gonna I assume that it's okay that I get started. So I'm gonna I don't think everybody's here, but it's starting to get a little late. So I'm gonna get started since you're all here and it's late at night, and I'm sure you guys would like to relax too. So I'm gonna start today's session. And if like yesterday, I did want to start today's session with whatever questions you might have regarding yesterday. Now, I tried to do that, but if some other questions come up regarding scientific explanations, then just let me know. Today, what we're gonna do is we're gonna move away from scientific explanations, and we're gonna go into another form of explaining, which is called developing models. So today we're going to introduce building models. Just like explanations will not be the first part, we will definitely revisit explanation building on Friday somewhat, and also modeling somewhat. And then next week we'll go even deeper into modeling, because we'll start to use Sage Modeler, and I'll give you some instructions on Friday about how to download that particular program. So again, I'm going to be monitoring the chat. Sometimes it gets a little bit hard for me to follow along totally, but I will do my best to monitor the chat as we go. And if I miss someone's question, don't feel like I'm ignoring you. It's just that it's hard for you. You might have to ask it, raise your hand and ask it, or just write it again. Sometimes it's just hard to follow all the chats while I'm also trying to talk. So I will try to do that, but I'm not exactly sure how successful I'll be. So today we're going to talk about modeling.
Excuse me, Joe. There's a question in the chat box.
I'm sorry, I didn't hear that. Say it again.
Oh, there's the question in the chat box.
Is there a question in the chat box?
Yeah. Yes.
Yeah. From high school? The answer is absolutely, I do. We actually have the interactions curriculum actually focuses is on a 9th grade curriculum. It's not 10 or 11. I had assumed we were working more at the junior high level, 8, 7, 8, 9. But I will certainly try to dig. I certainly work with. That's my own personal background is high school chemistry. So I work in high school chemistry, and I will. And we have some units from the crafting, engaging science environments that have kids write explanations, and I will try to find those, and I can try to share that with you on Friday. I'm just going to make a note of that. Okay, I don't see anything else. So today, what are we going to do today? Well, we're going to build some common understanding of how to support students in building and revising models. Modeling, like explanation, is a really important scientific practice. Students' models of the particle nature of matter develops across time. We might spend that particular time more on Friday, but we'll see how far we get today. I wasn't quite sure. And then hopefully we'll also have some time to respond to questions and comments at the end. I do have to leave a little bit earlier today. I have to leave at my 10 to 9 rather than 9 a.m. because I have a meeting with my dean that I need to get to on time. So we'll end a little bit earlier today than normal. So that's what I plan to do today. Again, please feel comfortable to ask questions either by raising your hand or by putting something in the chat. And as I said, if I'm talking too fast, somehow also let me know. I tend to get excited and then I start talking very, very, very fast and people can't understand me. So what you'd like, if I start to talk too fast, please let me know. Okay, so again, I'm just trying to show you why this is so important. And one of the things, science education, both in the US and globally, have changed. And one of the things that we have to do is engage students actively in using scientific and engineering practices, along with disciplinary ideas and cross-cutting concepts, to get them be the individuals who really are the ones who are developing the knowledge, are actually doing the science. And that's very different than how, at least when I first started to teach, and also when I went to school, it was always someone was telling me the science rather than me figuring out the science. But the world, we now know that if we're really going to develop a group of students who really can really understand and do science and solve the pressing problems we have today, like climate change, like sustainable food, like sustainable energy resources, then we really have to engage them in the ones who are making sense of ideas in classrooms. That means we're not going to necessarily cover all the information we did, but covering doesn't lead to understanding. We want kids to develop their own understanding. So why we as teachers might not cover as much, the kids will really know a lot more. So this is just a quick review from yesterday. Major shifts in science education across the globe, a big focus on explaining phenomena and designing solutions to problem. This notion of developing competencies where kids can use scientific ideas and practices to really make sense of the world. Coherence, making sure that we build across time. Yesterday, I ended with saying, look at how value would be for kids to start building explanations early on and then going through to high school. That's coherence. And then lastly, this notion of if we engage in explaining phenomena using three-dimensional learning, kids will develop usable knowledge. Again, they're the scientific and engineering practices, as I pointed out yesterday. There's a variety of them that all tend to work together, and modeling, developing and using models is one of them. Now, one point I didn't mention yesterday is notice this list. This list doesn't say students memorize models. It doesn't say students can recite explanations. It says students will develop and use models. It says students will construct models. This is when we talk about the scientific practices, it's extremely engaging. It's having the students do the work. Three-dimensional learning, again, is a notion of incorporating the big ideas of science, both disciplinary ideas and cross-cutting concepts like cause and effect, along with scientific practices to really try to understand the world, explain phenomena, and design solutions. And once again, these ideas, when they work together, are exceptionally powerful. It really gives us lots more strength in being able to do something. Every little strand in this rope has something, but when it's twined together, it really is much stronger and students can do a lot more. And that's the vision of three-dimensional learning. So what's today's performance-based learning goals? I think you might remember that I love to express things in terms of performance-based. And so today what we're going to do is we're going to develop a model to describe that matter is made of particles too small to be seen. And so this is a middle school objective, at least here in the United States. So we're going to develop a model that describes, sorry, I must have left something out. So we're going to develop a model to describe a phenomena, and we're going to get involved in that. So what is a model and what's modeling? What I'd like you to do right now is we're just going to take 5 minutes, 4 minutes, let's say 4 minutes, and go into a breakout rooms and just discuss what modeling is. And then what I'd like you to do is when you come back, I'd like you to put in the chat what your group thinks a model is. So we'll go in the breakout rooms and we plan on coming back in 4 minutes. So can we get put in the breakout rooms?
Yep. Okay.
Are we breaking off in the, I guess we are. Okay, so we still have to get some people to join some breakout rooms. Breakout room 2, 4, and 5 are open. So hopefully some people will join those breakout rooms. Please join your breakout rooms. Okay, can we close the breakout rooms? I can't seem to close them today. Yesterday I was able to close them, but today I can't. So if you could please
Oh yeah,
close the break.
I'll assign you as a co-host. Sorry, forgot to do
Okay.
that.
Yeah, I still can't close them. So if you could close them, it'd be great.
Yeah, I already did.
Okay, great. Thank you. Yeah, I think we're all back, or I think most of us are back. So if you could put in the chat, here we got group 1. Group 1 points from discussion illustrates an idea, something can use to explain concepts representations, they represent a concept, help students imagine abstract things, visualize something, describe what is in our mind from a viewer, describe what is in our mind, viewable by others. So it has to be viewable by others. So group 3, a model is a representation of ideas, objects, events, processes, and systems. So those are all really on point about what a model is, right? So models actually try to provide an explanation of what of some phenomena or some problem. So then finally in group 3 said, developing a model is using or creating a model to represent objects or a thinking process. So those are a nice little warm-up to get us to think about what a model is. So as your comments said, models serve the purpose of being a tool for thinking with, making predictions, and making sense of experience. So that's pretty close to some of the ideas that I just got done reading. And further, scientists use models to represent their current understanding of a system under study, to aid in the development of questions, explanations, and to communicate ideas to others. Now, this first part, their current understanding of a system, is really critical because, as we know, models can change as we develop more evidence. And so we had some pretty good models in the past of how the world worked, but as we gather more information, models change. And that is such a critical aspect to realize. So developing and using scientific models, their representations, they represent the objects and the relationships among them to explain and predict. So that's what a scientific model is. It should provide a causal mechanism, right? Causal mean something impacts something directly to cause it to happen or to make it happen. It could be picked as a drawing, a diagram, three-dimensional object, right? We can build a three-dimensional object or other representations. One of my fascinating reads as a young student was reading the story of DNA and how Watson and Crick tried to build a three-dimensional model of DNA, but they had it backwards. So if you've never read the story of DNA, it really is a fascinating story of Watson and Crick and Rosalind Driver, not Rosalind, what's her last name, and the female involved, really trying to build a model of the structure of DNA based upon the evidence they had. So it's a really fascinating reading if you never read it. But only represent, and this is critical, only representations that explain and predict phenomena or provide a solution to a problem are scientific models. You can always have representations, a drawing, but unless it explains, it's not a model. And that's critical for us to understand. So models explain and predict how and why phenomena happen. So these are some steps, but we want to go beyond what is a model, and we want to be able to develop models. And so these are steps in developing a model. So the first idea is you have to plan. And when you plan, you need to think about what objects or components, right? So what objects or components do you need in your model? Another way of thinking about that is what factors and variables that are associated with those objects, right? So what's inside your model? What are the big parts? Then you need to build relationships between those parts. So what relationships exist between each of the factors or variables? Then we have to test those set of relationships. Do those set of relationships actually provide a causal account Does it explain the model? Does it account for all the evidence that you have? And then the last part in any model is actually to revise based upon your testing. And I'll show you a clever way of testing since a paper and pencil model. You usually try to revise your model based on feedback. So we'll see if we can't go through that process today. Okay, so I'm gonna do a really simple example of how to make a model. So I'm gonna stop sharing this, and then I'm gonna go to my whiteboard. I'm gonna create a new whiteboard. And I hope everybody can everybody see the whiteboard?
Yeah, we see.
Oh, good, thanks. So I'm gonna draw a model, and every model, like an explanation, always begins with a question. So I'm going to start, this looks different than I had last night. I'm gonna start by this is different than what I had. Huh. I don't see the tools in here. This isn't like my whiteboard. Does anybody see the tools?
The tool is not on the left-hand side. I see the tool on the left-hand side.
Yeah, I don't see any. I see no tools. This is my left hand. That's my left side, right? There's no tools. And there's no tools over here as well.
Can you see it drawing something?
I
the
don't
board?
see. I don't see any tools.
Oh,
I'm trying to find the tools to draw something.
You
Yeah.
did you draw? I mean, not Professor Joe, but Burin. I think you draw, right? Something.
yeah.
Here?
I draw the curvy line in middle.
So
Yeah,
you
but
just
I don't
using the
see.
mouse.
I don't know how you did it. I have to be able to do it. This isn't like the one I practiced last night. This doesn't look like mine. Okay, that's okay. I'm not going to worry about it. I will just talk you through it. How's that? So I'm gonna
Maybe host only can.
well, I'll tell you what. Can someone draw a little circle? Who can draw a circle? Can our host draw a circle? There we
Okay.
go. Let's move the circle. Oh, no, I like it the way you had it before. Make it small,
Oh.
like you did. And we're going to answer the question, what affects my grades, right? So think of you're a student, and we want to answer the question, what affects my grades, right? So we have to put as an outcome variable on the right side, one of these circles, and inside that circle, boy, this is awful. Why can't I use this? Inside that circle, we want to put, we can type my grade. So can we do that? That's my outcome. That's what I'm trying to explain. How do I get good grades? Very good. And let's move it over to the right side. Can someone move that whole thing all the way to the right side? Oops. And now I want to ask everybody a question. And whoever can draw on this tool, let's do that. What factors, what variables affect your grade? You can type them in the chat. What factors affect a student's grade? I picked this example. Okay, number of revision hours. Okay, that's good. Let's type that. Let's put that on the side. That's one of our factors that affect my grade. Reading time, okay, is another one. Let's put that on. Let's put that in our whiteboard. Attitude, okay, positive attitude, attendance. Those are all factors that affect my grade. Teacher feedback, very good, I like it. Teacher feedback. My performance, of course, my performance is intermediate to my grade, right? So all those factors influence the grade I'm going to get in my class. And of course, if I was going to draw a model, because a model is a representation, I would have each one of these in a circle and then draw a line to represent that connection. And so we would then have a paper pencil model of what explains my grade, right? So can someone draw a line from feedback to my grade? How about a line from feedback to my grade? Very good. And how about a number of revision hours? Can someone draw a line from it to my grade? And what about reading time? Reading time to my grade. And of course, we could put some of those other factors in there as well. We could put and now we got attitude. We could do the same thing and draw a line to attitude, attendance. Okay, I think that's good. Very nice. So it was a nice group project. Not sure why I don't have control of those tools, but I think we did a nice job drawing our model. So this is a beginning model of what a visual representation that it can explain my grades, the number of revision hours I spend, the amount of reading time I spend, my attitude, the feedback I receive from teachers, and my attendance. And of course, we have some other ideas also in the chat related to this, like how I feel. If I'm healthy during the exam, I'm going to do much better than if I'm not, right? If I'm sick, I'm not going to do as well as if I'm not. If I do well during the class, I'm going to do better. So we could add those other ideas, and that would lead to all the factors. We've now shown a variety of the different factors related to my grade. Now, one of the ways, so we just built a simple model. And what do I mean by that? Well, we put down all the various variables that could possibly affect the phenomena of my grade. And so I would, now it's a paper pencil model. So it's pretty hard to, we can't really test it numerically in any way. But I did draw a simple model, and I can now ask myself, does it really explain my grade? So for instance, if I took out the number of revision hours I spend on my homework, would that affect what would happen to my grade if I just took out number of revision hours? What would happen to my grade? I would assume it's probably going to go down. So we can remove some of these factors, and some of those variables. And if we then say, by removing a variable, does it affect my grade? Then we know that it's an important thing to keep on. Right? So for instance, if I put down, if I was just being funny or kind of silly, and I wrote down my clothes, the clothes I wear don't affect my grade. So that's not an important variable. So if I had it on my model and I took it out, it wouldn't affect my grade. But all these factors that we put down, my attendance in class, my health, the feedback I receive from teachers, my attitude, the time I spend reading, my work hours, and the number of hours I spend on revision, those are all ideas that affect my grade. And if I take any one of them away, my grade's going to go down. So they're important to keep inside my model. Okay. Any questions on that very simple model that we just draw? I was trying to think of a simple situation to get us to come up with drawing a model before we went into a more complex example. Okay, so when I'm going to close this. I'm going to share my screen again. So just remember, in building a model, we always want to say, what are the objects or variables that are in my model? What's the relationship that exists between each of those variables to predict the outcome measure? And then we're going to test it by removing some of those factors and seeing what happens. So those are the critical steps in initially building a model. Excuse me. So now we're going to go into a scientific model. And this is one, it's called, we're questioning, is air matter? How do we know? Does air have mass? Does air occupy volume? Oh, excuse me. I'm sorry about that. Let's find out. So we're going to do a little bit of science, and we're going to see again, this is a 6th grade, 7th grade unit on the structure of matter. And so we're examining, does air or do gases actually have mass and occupy volume? So here's a little, I'll show you this better because it didn't come out as nicely as I thought. You can put air inside a flask of some kind. I have a syringe instead. So inside my syringe, you can put some air, and I have some air inside my syringe. You can remove some air, and I can add some air, right? So I can do all these kind of things, put it into my syringe. Now, so we know some things already because it's always these are the things we've studied already. Matter is anything that has mass and volume. Air has mass and occupies volume. Air can be subtracted from a container. More air can be added to a container. Matter can be solid, liquid, or gases. Those are all the things we know so far, right? So we know that matter is anything that has mass and volume. Air has mass and occupies volume. We can take it in and out of a container. And I know I can take it in and out of the container because I can sort of feel it when I do this. And matter is a solid. So we're now going to build a model. how can we model the things that gases do? So I'm gonna fill my syringe halfway filled with air. Now I'm going to do something really important. I'm going to put a cap on the bottom of my syringe. Hopefully everybody can see that. I'm putting a cap on my syringe and I'm tightening it. You can also do it with your finger, but it's easier if you have a cap. So I put a cap on it. Now, when I do this, I'm just going to ask you some questions. So remember when I had it off, when I had the cap off, it was really easy to pull the air, take air out and put air in. I had no problem. Very simple. In and out. Now I'm going to fill it halfway and I'm going to put the cap on. Now when I try to push it in, what's going to happen? Is it going to be easy for me to push it in or hard for me to push it in? Obviously, I wish we were in person so you could all try this. But if I try to push this in, I can't push it in all the way. I'm a pretty strong guy. And I think you can see I only can get just a little bit. I can't get all the way down to the bottom. Why not? Why can't I get all the way down to the bottom? And when I let go, it sort of goes back to that middle position. Now, when I try to pull it out, same thing. I can't pull it out. It's really hard. And when I let go, it goes back to the middle position. That's the phenomena I want you to explain. Why is it that I can't push my syringe in all the way? And I'm a pretty strong guy. I admit I've gotten weaker through the years, but I'm still pretty strong and I can't push this all the way in, no matter how hard I try. Similarly, it's very hard to pull this out. And when I pull it out, it snaps back. What's going on?
Because of pressure.
Pardon?
Pressure.
Yeah, questions in the chat. Hold on. Forgot the monitor.
Area pressure.
We have some comments in there about it's hard, pressure, air occupies the space inside the syringe. So this is what I want you to do. We're going to go back in our breakout rooms. I'm going to suggest that there's 4 or 5, 6 people, not more than 5 people or 5 people in a breakout room. And I want you to draw a model because we're trying to explain what's going on, right? That's the goal. What's going on? So in the first model, and this is all in your PowerPoint, so you can see it. We have it when it's half filled, right? And it's capped, right? So what does it look like if I had this very powerful microscope and I could actually see that air that's inside here? What would I see? And then when I push this in to the middle position, what would I see? And after I pull it out, what would I see? That's your goal, to construct this model of air. That shows why I can't push it in, shows why it comes back out, and shows why it's hard to pull it out and why it pushes back in. So this is the model I'd like you to draw. And so we're going to go into our breakout rooms. I'm going to give you about 10 minutes because there's 3 models to draw. Maybe I'll give you a little bit longer. I'll think at 10 minutes, I'll drop into some breakout rooms and see how you're doing. And then if you need more time, I'll give you more time. But what we're going to do is you're going to draw your models, these 3 models. Then you're going to come back. I'm going to ask one group to share it. And we're going to talk about how you can critique models. And then based upon the critique, depending on the time, we'll drop back into the breakout rooms and we'll have the groups revise their models based upon the critique of that one group's model. Are there any questions about what people should do? Okay, let's go into our breakout rooms. Again, let's get 4 to 5 people per breakout room. And I think that would be great.
You are muted. Microphone.
I said I apologize for getting back a little late, but I was stuck in a breakout room.
Yeah.
And I didn't realize I was in another breakout room, and so I had to say leave. So anyways, I'm here. Great. So I'm hoping now, I think everybody's back. We're getting there. I'm hoping that we could have, let me share my screen again, and then I'm going to have a group actually share their model. I failed to mention this important aspect. What's your task? But that's okay. Everybody seemed to, at least the breakout rooms I got into, people were doing their task. So it's, one of the ways I like to introduce modeling to young students, let's say you're in 7th grade or 6th grade, is rather than initially saying draw a model, I like to say draw a picture or draw a series of pictures that shows why. In this case, draw a series of pictures that shows why you could expand and compress the air that is in the syringe, right? So that's one way I could do it. Now, if the kids know about models, then I could say construct a model or then I could say draw a series of pictures that provide a causal account, right? So I'm going away from just why you could expand to using the word a causal account, like what's really impacting it. And then I can move away from using the term picture, then I can say construct models that provide a causal account. So there's a variety of ways in which you could scaffold it. You could say draw a picture, that shows why, draw a series of pictures that provide a causal account, construct a model that provides a causal account, a causal explanation. So there are a variety of ways in which you can express it to your students. I've always had luck the first time I've done it with a new group of students to say draw a series of pictures. And as I explained before, all models start with a scientific explanation. In the case we just got done with, I was asking all of you to draw a model to explain why it's hard to push my syringe in, why does it pop back out, and why is it hard to pull it out, and then it pops back in. So that's my scientific question. All models provide an explanation. So the model you drew should provide an explanation of that phenomena. We want to begin by identifying the objects, the components and the variables that are important in that system that we can't see. And then we want to make sure we specify relationships that are there. And then we need to ensure that the collection of relationships actually explains or accounts for, tells us why that phenomena actually occurs. So at this point, I jumped ahead too fast in the model. I would like to have one group share their model. So could I have a group share their model? And what I'd like to do is I'd like to use these criteria to describe, to give people feedback, right? So is it accurate? Does the model actually account for the phenomena? Are all the right variables there? Are the relationships there? Right? So does the model account for all the evidence that we have? In this case, our evidence is, I know it gets hard when I push it in, it pops back out, and it's hard to pull it out and it pops back in. Is it useful? Can the model illustrate and predict? Is the model clearly labeled? Does the model only include necessary information? And does the model include all the key components and relationships? So using some of these criteria, I'd like one group to share their model, and then the rest of us to give them feedback on it. So who would like to share their model?
We want.
You would? Someone would? So go right ahead. Sure. I'll stop sharing. and some other group can share their model, and
So we used simulations. So I want to start our explanation just that air has molecules. So molecules everywhere. And air has a pressure. So firstly, the pressure inside the, for example, this cylinder and outside it are the same. But when you push a piston, let's say it's a piston, you can see the indicator of pressure. So when you push, the distance between molecules are getting closer, getting smaller distance between. So pressure increases. So pressure can be more than outside. And just against, if you go to the opposite side, you increase the volume. When you increase the volume, you decrease the pressure, because increasing volume means decreasing the number of interactions between them. So decreasing pressure means it can be less than pressure outside. So air pressure doesn't give you continue to, I mean, to this side. Go to this side. This is our explanation.
okay. What does everybody else think of this model? Any comments?
May I?
Go
You
ahead.
can go first with the.
Please go ahead.
So for me, in my opinion, this model would be able to explain the situations that we are explaining, as well as it's actually suitable for students that are in higher grade compared to the lower grade. So students or pupils at the younger age might not be able to understand pressure concepts, as well as the distance between the methods. So with the concepts being including pressure inside, it is possible that this model is suitable to explain for the higher age students.
Right.
It depends on level. Yeah, I agree.
And any other question? Any other comments?
Yes. I think this is the good model to illustrate how the pressures and volume interact with the gas. But this is this model is the closed model. But the model in the series, it's an open model, so we can predict what the gas inside the series.
Yeah, we can predict, that's correct, what's inside there. What other comments? See if there's any chats. You can also put your comments in the chat. So we have a comment here. A model is a representation. Oh, that was before. Okay. No comment here. So, this is an interesting model. But it's someone else's model, right? This is the scientific model that someone else developed. And the goal of today is to get kids to develop models, not to use someone else's model. So this is very accurate. There's no, well, in fact, there's a big inaccuracy in this model, and I'll specify that in a second. But other than that one factor, this is a very accurate model. But it also is someone else's model. It's not the kids model. And the goal is to try to get kids to figure it out on their own. So from my teaching perspective, I would first have the kids draw their own model to see what might be causing this. Because when kids can construct something on their own, that's how they really form knowledge. In this particular case, they are manipulating variables, but they're not actually building the model themselves. So I would really encourage, so there's, I would show this at the end, right, as another example of. But from my perspective, there is one major error in this model. Does anybody know what it is?
May I show something? I'm not sure how correct it is.
You need
May I
a
share?
screen share?
Yeah, you can share your model. I just want to notice that in that past model, what's missing are the air molecules on the outside. So we saw the air molecules in the inside,
Yeah.
but there's no molecules on the outside. And that's the error in that past model. Let's see this model.
I know, I just draw quickly on my iPad. So first of all, in first model, we know we kind of pulled in some air, and a third grade student will know there are air, right? Air or gases or something. And then you close that syringe and you block that gases in it, and you made the closed space, and there are no place to go the gases. And the third one, because those air is closed, it kind of how I'm gonna say, not create the pressure in it, and that's why when you pull out the how do you say, the portion or something, there are no place to go.
Piston.
Piston. So I know how correct it is, how right. In the first, this is a different type of gases. With our group, try to say there might be air, there might be another type of gases. That's why the different color, but that it is. So I think that's
Sure.
a simple explanation for third grade and quick one.
Right. So I'm curious about if you push it, so using your model that's on the left side of a mixture of oxygen and nitrogen and carbon dioxide that make up air, right? Air is always made up of a mixture of gases, oxygen, nitrogen, carbon dioxide, primarily. And now if I took it and I pushed it in, how would this look different here? That's the important
So if in the first model there are different gases, right?
Mm-hmm.
So, and you will push in. So
we push it in like that you have here, right? What does it look like if you push it in? What would be different between the model on the left and the middle one?
So the gases will go out in the first one, and the second one they closed, right?
Yep, it's closed. And what would the image look like?
I didn't get, you mean this image? Here, I see. Oh, yeah, I got you. So you mean the gases? So let's imagine this is a model. There, half of them will be like a pressure. So we like this. Oh my gosh. So and then all the gases will be in half of the space, in the half of the model. Am I right?
Well, they will be more compact, that's for sure.
I mean,
Right?
so if I will imagine that's the balloon or the lung, and we will exhale the air, so it will compress the lung, and then and it will like yeah, get together. No, more pressure for the one side of the balloon. Let's say, like if it's balloon.
I'm just going to raise a couple. So this is the reason I like modeling, and it doesn't work as nicely on Zoom. I wish I was there with you so you could actually feel this. So when the syringe, I'm just going to ask you a couple of questions. When the syringe is in this configuration, right? So I'm going to take the little top off, and now it freely moves back and forth. And I'm going to put it so that it's the halfway mark. And then I'm going to I'm going to close the cap. I'm going to ask you a question. Inside my syringe, as you pointed out, there's air in there. Air is made up of different type of molecules, oxygen and nitrogen, carbon dioxide. Now, the question becomes, when I push it in, does the number of particles change?
No, number
No.
doesn't change.
Number
Constant.
doesn't change. What changes?
The distance
Distance
between the
between
particles.
The distance between the particles. Why? Because what's changed in the syringe is the volume that they're in. So that's what you need to represent, right? So the total number of molecules don't change, but the area in which they're in does change. Now, so that's your hint about if, I'm not going to tell you if you're right or wrong. I'm just going to give you a hint. That was my hint. And there's another group that said they would love to share their
Yes,
Yeah,
the group two.
let's
Yeah.
share the other one.
Okay. These are the answer of group two. So the first picture is, so if we pull out the number of particles go inside it here is equal to 4. When we press it and the top is the closest, so the distance between molecule is like they closer than each other. And then when we pull out again, so the number of air is equal to the first, but the distance is more wider than the second one. So that's it. So the second group, it is not surprise because we have 3 chemistry teachers in the group too. Okay. Okay,
I'm
that's it.
happy.
Okay,
Yes,
that's it. Number 2. Yeah.
There was a comment in the chat saying, I like this one. And any other comments about this particular model, even though there's 3 chemistry teachers in the room, in that room?
So, okay, group, so you can comment because we maybe 3 misconcept teachers here, so you can comment. Yeah.
Yeah, maybe I can give some additional information. We put the same color, so we think that the student at school will just only think that as air particles, not the molecule or something. That's why we put the blue circle, the blue models, particle models, and then the same number of particles on it. Yes, that's the additional one.
Probably John mentioned about the volume, then show the volume, like when it, I'm gonna say explicit, and then like expanded this thing, because like it's pretty, it looks like just like similar to each other and show the differences. I guess that Joe was asking me the same thing. Am I right?
Yeah. right? So the goal here is that you get the same number of particles, but they're in a smaller space. And because they're in a smaller space, it's much it's harder to push them in even smaller because they're bouncing back and forth so often. But I think Peter had his hand up, so I want to call on Peter to see he had a comment. So Peter?
Yes, for Model 1 and Model 3, currently what we see is basically they look quite similar, although for the fact that we are supposed to give two different models. In a sense, one is actually the regular without actually pushing or pulling, while for Model 3 it's supposed to be when we pull it. So likewise, I think the model should be further apart. I mean, the molecules or the particles should be further apart rather than they are quite similar in distance with Model 1. That's all.
Yeah, I wasn't, that's a good point. In the way I explained it, you know, this is much farther apart. If we expand it way back here like this, then the particles would be much, the particles would be much farther apart. Right, so if I expand it from that position, the molecules up here would be much farther apart. And I couldn't quite tell, if I look at the drawing actually that I gave you, this one and this one are pretty close. So I thought that's why they were drawing them similar to each other, right? So
Yeah.
not necessarily doing what I did, but doing what shows in the syringe, right?
Because
So
the volume of the syringe, Joe, because it looks the same, the first and the
yeah, the first one and the third one are the same distance, and that's
Yeah.
why I thought you didn't have it spread out. But in fact, if you did do it, you know, pull it way out, then there would be they'd be further apart.
Yeah.
Anyways, one of the points. Any last question or any other group want to share? Make group yes, group 4 can share their model too.
So
one
yeah, this is our group 4. Our model might not be quite accurate due to the reasons that the number of air particles inside are not similar. We sort of like drawing based on the distance of rather than I haven't actually calculated how many particles are in each space. So yeah, that is the main problem that we face. But the thing is, yeah, for model number 1, the distance is quite relatively close but not further apart. But when we push the plunger in, it was be very close. Means all the particles becomes very compact. And when we pull the plunger away, the distance between them becomes further apart, and yeah, the number of particles is supposed to be remain the same. Yeah. So what we are having right now is the number of particles might not look the same. And we label the air particles to be generalized as air particles by itself only. It's not like there's carbon dioxide, there's water molecules also, oxygen, and yeah, that is the general idea. Thank you.
Right. So thank you for sharing. The question that we always try to answer, does the model actually explain the phenomena? And there is a comment in the chat that says this one definitely looks like one of the this one actually looks pretty good, right? So it doesn't, if it's accurate, or with the question about accuracy, does it explain the phenomena? And we can look at all the models that we saw, and we want to ask ourselves, well, in this position, right, if we imagine air as being made up of tiny little particles, then we would see the air all spread out in this aspect. When I push this down, they're going to get bunched together. The number isn't going to change, but they're going to get bunched together, right? The number never changes, the number of particles, because I didn't take any or put any in. But what they do is they end up being much more compressed into a smaller space. Then when I pull it out, the number doesn't change again. They're just spread out. So the question is, does any of your models actually provide a causal explanation of that? And this is the fairly, why at first glance, it seems like almost a simple phenomena. It's actually a fairly complex phenomena. And this is why having kids try to draw and explain it, and often using words along with the drawings actually help learners to explain these ideas. And this is very important. I'll come back to the picture that's in the drawing in the chat in a second. Very interesting. So we always want to ask ourselves that question. Can you stop sharing your screen, please? One of the points I want to make is that when kids draw models, it really helps. It allows them to present ideas to their other classmates. It also gets them engaged in collaboration and talking. And when kids can talk about their ideas, just like when I was talking through the model with, where'd she go? I think it was the first one we looked at, and the second model we looked at. When we talk through that second model, it helps people when they're talking with their peers and with each other. It actually helps them develop their understanding, and that is so critical. So one of the reasons I love model building and art is because it gets kids engaged in discussion. Now, interesting enough, one of the models I was going to show you is currently in the chat. So I'm going to bring it up. I actually have it on my computer. So I'm going to bring that up. And then I'm going to share my screen. And I think everybody can see that, right? This is actually a model from the Concord Consortium. It's actually part of the interactions curriculum, interesting enough, because we want to make sure kids understand it. And this is a model that basically allows you to do what we just did, but it shows you what's happening at the molecular level. And I love for kids to do that. It's okay to show them at the end, right? But this isn't their model. This is someone else's model. And of course, kids can't develop something as complex as this because it takes quite a bit of programming. But this is kind of a fun little model. It's not as sophisticated as the first one we saw, but you can remove the stopper. And one of the things I like about this one is that you can see both particles inside the syringe as well as outside. And of course, then I can sort of pull back the thing. And I can lock it in place. I'm going to just push it in a little bit and lock it in place. So now it's locked in place. I'm going to add a stopper. And so what you see is what I like about it is you can see the molecules pushing on both sides of that plunger, right? So now when I try to push it in, you see how it gets more compact. And that's why it's so hard to push in farther. And of course, the reason why it gets hard, if I try to push it out, pull plunger out, the reason why it's so hard to keep pulling it out is because there's more molecules hitting the one surface than in the inside. And so this is, that's what's going on here. So this is a pretty nice simulation. This is part of the Concord Consortium, collection of artifacts. I believe the one we saw before was from FET. Is that correct? Who showed model one? Was that a FET simulation?
Yeah, it was a FET simulation.
That's fine.
So both FET and Concord have very, very nice simulations that you can look at. Okay, I'm going to go back to my PowerPoint. Oh, no, that's not what I wanted. Stop sharing. Going to go back to my PowerPoint. Okay, I'm just gonna stop and I'm gonna stop and see if there's any questions on modeling. You can put them in the chat. If we don't have enough time, otherwise I'd have you go revise your models. I really think revising models is really critical in the process. But just like building explanations, constructing explanation, just imagine if we had kids constructing models from K2 to high school, we would have very different learners. One of the challenges of today is to get kids who can use ideas to create new things, not just use someone else's models, but build new models. If we want to have our societies be very rich, pushing the really trying to come up with innovations, then we have to allow kids to innovate, and asking them to draw models based on evidence is really critical. So one of my goals, one of my hopes is, once again, to get kids of all ages drawing models. It's challenging. Now, today, we sort of abstracted, you know, a small part of a unit, a full unit, and I asked you to draw models. So we don't get the whole image. But the point is that in a class, when you have sequential lessons, getting kids involved in drawing these models is really critical, because that's what leads them to be able to create things, to be innovators, and to form much deeper understanding. And you're absolutely correct that it will take time. It takes time away from classroom. It takes time away from you as a teacher to cover material, but it doesn't take time away from kids in learning. When kids actually build things, when they construct a model, and they had some of the same conversations we had, like, is this right? Does this really explain it? What would you add here? What would you take away? When you get them involved in those kind of conversations, does it really explain that phenomena? When you give them that sense of them being the developers, or them constructing the knowledge, that's what gets them to be really cognitively engaged, which will lead to that deep learning. And so it does take time away from normal classroom instruction, but it doesn't take time away from kids developing knowledge. And that's what we want them to do. And we can't just think of knowledge as it's a developmental process from kindergarten through high school. And I also have models. I also have models from high school, which I will share with you as well. So what does modeling mean for middle and high school students? Because that's what we deal with. But I've also very successfully drawn models with kids in I can't say second grade, but I have worked with them in third grade and fourth grade and fifth grade, and they can actually draw very sophisticated models in those grades. And so we always want them to start with a question that's based on a phenomena, like I tried to do today. And we'll go deeper into this as time goes on. The goal should be to develop a model to show how this happens, why something happens. You want to make sure you have the evidence. Does it fit the evidence? So for instance, when I push this in, my evidence is that it's really hard to do so. And of course, showing those molecules really hitting the surface, pushing it back, provides that evidence, right? So you always want to make sure it fits the evidence that you have. And when I pull it out, of course, the tendency of the syringe is to go back in, because there's more molecules pushing it back in. And we always want to compare models and evaluate how well they explain respond to our question, and can we as a group actually reach consensus on it? And of course, as teachers, we always have more knowledge than our kids, so it's always hard not to, you know, my tendency is wanting to give them the right answer, but that's not what's going to form that deep knowledge that we really want our children to have. So I will show you some examples of some kids' models later on, but because of time, I have a meeting with my dean. I'm gonna have to just cut this a little bit shorter today. So I want to see if there's any questions that I can answer before we take off. Otherwise, I'll give a quick wrap up and move on. Any questions? So we do have to figure out, thank you for saying no. The modeling activity cannot isolate from content. You're absolutely right. This is that whole point. You can't separate modeling from content understanding. But when you build a model, it helps you form that knowledge. This is why I said it was wonderful to read the book about, if you're a biologist, no matter what area of science you're in, picking up Watson and Crick's, picking up a book about Watson and Crick first developing DNA is really fascinating, because we all know, you know, if someone said to us, what's the structure of DNA? We would always say, oh, it's a double helix and hydrogen bonds are holding it together. But when Watson and Crick developed that model, they had no clue. And of course, the first model they built was all wrong. And their director of their lab said, you guys are ignoring fundamental science, and kicked them out of the room. And that's always the process of model building, right? So model building always, it's not a simple task. It's a very, very challenging task, but it not only helps you, it does interact with our content, but it also helps us build our content. That's what Watson and Crick did. They helped us build our knowledge of how DNA was actually put together. Now, they obviously came with some understanding, but as they built that model, they actually formed new understanding. And that's the whole point behind model building, is when kids build models, they also construct knowledge in their head. When a kid can draw a model that can explain why this is so hard to push in, they're really forming that deep knowledge. So it says, in order for students to draw air particle model we did today, what are the prior knowledge that they should already have? So you're absolutely right. They have to come in with different understandings. This was actually part of a curriculum that the kids did develop some understandings prior to this. And as I said, they knew that matter was made up of particles. They know that air is moving around, so they know all that stuff. And so they're just trying to, now once they know that air is made up of tiny little particles, they have to explain why it gets harder to push this in than to pull it out. So there's always knowledge that kids come with, but it then helps them build more knowledge, right? So they come with the knowledge that air is made up of tiny particles, but they realize that it fills the space, right? So air is made up of tiny particles, it fills the space, but then they come up with their own understanding that because it always fills the space, as I decrease the space, then it gets harder and harder to push them together because they're actually pushing back on it. So that was the new knowledge they actually developed. So with that, I'm gonna call today. We're gonna end today a little bit short. On Thursday, Anne is going to meet with you and continue with the water quality unit. I believe she's going to do some discussion of explanation. And then on Friday, we're going to pick up our discussion of modeling. And I'll also share with you a rubric and some student examples of explanations. So you can see how that works. I'll try to find some high school examples of explanations and also models. And then what we're going to, and I'll finish off, I'll show you this further examples here as well. And then next week, we're going to dive much deeper into modeling using an online program that will still allow you to build models online. That's right. If you I'm assuming Mohammed, I totally understand. If you're not a science person, it's really challenging. The question was, I'm going to just answer this question, then I really have to take off. You never want to be late for your dean, unfortunately. So one last question. Apart from the CER model, are there other methods to enhance scientific explanations? I don't know of any other techniques. It's used all over the US and in other countries as well. I know it's used in China, for instance. So I don't know of any other techniques. I do know that and I'll talk about this next time as well. It's really important as you move into high school to fade away the scaffolds. So you really want the children, the learners in high school, to be able to write an explanation on their own. But even in high school, when you first begin, you want to give them that structure, because otherwise you're not going to know what an explanation is. We have to be very explicit in helping kids understand both what an explanation is and what a model is, because both of them are so critical for forming understanding. So with that, tomorrow night you have a free night. We're very busy this week. We 4 nights you guys are here. You're very dedicated in your work. I want to thank you for that very much. So tomorrow night your night and my morning, we don't have a session together, but then we'll see each other on Thursday, where Ann will do the water quality, and then I'll come back with you again on Friday, where we'll go a little bit deeper into explanations and a little bit deeper into modeling. So have a pleasant evening, get a good night rest, and then I'll see everybody on your Thursday and my Thursday morning. Bye-bye.
Bye.
Thank you.
Thank you.
Bye.
Bye, everyone.
Yes,
Thank
thank
you.
you. Thank
Bye,
you.
everyone. Bye.
Bye. Have a good evening.
Bye.
Thank you, sir.